So now let's go back to the properties of hardened concrete. So now we are finished discussing the short-term or instantaneous properties of concrete. So now let's go to the long-term properties or long-term categories or category. So the first on the list is creep. So actually in actual, creeps looks something like this, the creep effect. So what do we mean when we say creep? Creep or lateral material flow is the increase in strain with time due to a sustained load. So that is the keyword here on the definition of creep. Strain with time, increase in strain with time due to a sustained load. The keyword is due to sustained load. So just like what I've been discussing a while ago, uh, the strain that comes immediately after you apply a load is what we call elastic strain. But if the material will support that particular load for a longer period of time, there will be a corresponding increase in strain, which is actually due to that sustained load. And that additional strain being experienced by the material due to that sustained load is what we call creep. The initial deformation due to load is the elastic strain. Actually, this is what I've said. While the additional strain due to the same sustained load is the creep strain. Yeah, that is what I have said before. So if we will try to imagine or if we will try to graph the relationship between the strain being experienced by the material, especially concrete, with respect to time, if we want to relate the two, we can graph their relationship using this curve here. So if we want to observe or investigate this particular graph, we can see it here that at a certain particular time here, actually the initial time, we can see that the material experiences a certain magnitude of strain, which is actually what we call the elastic strain. So uh, the material immediately experiences that magnitude of strain as the load is applied to the material. But if you can see here, that strain is instantaneous, meaning it occurs at a very short period of time. Actually, in a certain period of time lang. But after some time, you can see here that there is an additional strain being experienced by the material. After it experienced the elastic strain, you can see here that after some time, the strain being experienced by the material increases. And actually, that additional strain being experienced by the material as time goes by, as it supports a sustained load, that additional strain is what we call creep. So you can see here uh, on the graph that the graph illustrates the increase in creep strain with time, and as in the case of shrinkage, it can be seen that the creep rate or the slope of this curve decreases with time. So you can observe here on the graph that uh, the rate of increase or simply the slope of this curve or graph here decreases as time goes by, as time increases. Actually, it reaches a certain limiting point here, certain magnitude, certain maximum value of strain. So creep reaches a certain magnitude of strain as time goes by, according to this graph. Creep can be determined only by deducting elastic strain and shrinkage strain from the total deformation. So you can get the magnitude of uh, uh, creep strain by just deducting the elastic strain and the shrinkage strain to the total strain being experienced by the material. So the total strain being experienced by a material is the sum of the elastic strain, this one, creep strain, this one, and the additional strain that we will study later on, the shrinkage strain. Stress-strain relationships for short-term loading lose their significance and long-term loadings become dominant in their effect on the behavior of a structure. So actually, if you will observe the magnitudes of these strains, you can see that the magnitude of the elastic strain which is a short-term effect from the loading, is actually significantly small compared to these two strains coming from long-term effect of loading. So meaning the short-term effects of loading is actually insignificant, meaning not significant anymore in comparison to the other strains being experienced by the material. So the long-term effects are more important or significant than this short-term effect. So this graph is actually a continuation of this graph here. So after this point, if we will try to unload the material, meaning we will remove the force that the material experiences, you can see here that the tendency, if you remove the load being supported by a material, you can see here that it tends to experience a sudden decrease in strain, in the total strain here. So actually, uh, that sudden decrease in strain being experienced by a material as you remove the load that is being supported by that particular material is actually what we call the immediate elastic recovery. So, uh, what do we mean by that term? Immediate elastic recovery. So meaning, again, we will just try to recap the loading history of the material. So when you apply a load to a material, tendency it will have an immediate strain here, certain magnitude, which is what we call the elastic strain. And then as time goes by, as the material sustains to support that particular load, it will experience additional strain, which is actually what we call the creep strain. But for example, for this particular period of time, that at this certain time, for example, if we will try to unload the material, meaning we will try to remove the load being supported by the material, the tendency is uh, it will have a sudden decrease on the strain that it experiences. So again, that sudden decrease in strain is what we call the immediate elastic recovery. So after that instantaneous recovery, you can see and here on the graph that there is a gradual decrease in strain. So actually the material continues to recover strain. So that gradual decrease in strain here is actually what we call the creep recovery. The extent of the recovery depends on the age of the concrete when loaded. When loaded, with older concretes presenting higher creep recoveries, while residual strains or deformations become frozen in the structural element. So you can see that older concretes tends to have higher creep recoveries. Therefore, meaning they tend to uh, they tend to more be elastic at some point. Although actually the elastic is not the right term, but older concrete tends to recover more strain as compared to more fresh concrete, because obviously the older concretes already achieved their compressive strengths. Therefore, they are more resistant uh, to further increase in strain. So when you unload that particular concrete material, it will tend to recover some strain. It will tend to have a decrease in the strain that it is that it experiences. And again, that sudden decrease on the strain being experienced by the material when you unload it is what we call the immediate elastic recovery. And then the recovery following that, the gradual decrease in strain following that immediate elastic recovery is what we call the creep recovery. So what are the effects of creep? So obviously, number one, it increases the deflection of beams. So that is one of the effects of creep. It increases the deflection of beams and slabs, and actually it causes loss of pre-stress. So later on our later chapter, we can see that creep can actually cause to uh, creep can actually be a cause to for the pre-stress force that is being applied to the concrete by the pre-stressing reinforcement. It can cause to lose some part or a portion of that pre-stress force being applied to the concrete element by the pre-stressing reinforcement. So later on, we will talk about uh, those losses of pre-stress due to creep. So later on, actually, on module 4, we will talk about more about that the loss of pre-stress due to creep. So that is one of the effects of creep: increase deflection. Another effect, actually, this is a particular effect of creep. The initial eccentricity of a reinforced concrete column increases with time due to creep, resulting in the transfer of the compressive load from the concrete to the steel in the section, which actually will eventually result to the failure of the column. So those are the effects of creep. Another long-term effect, or long-term effect, another long-term property of hardened concrete is shrinkage. So it looks something like this. So there are two types of shrinkage: plastic shrinkage and drying shrinkage. Plastic shrinkage occurs during the first few hours after placing fresh concrete in the forms. So actually, comparing the two, plastic shrinkage is not actually that important and significant. What is significant here is the drying shrinkage. And what is drying shrinkage? It is the decrease in the volume of a concrete element when it loses moisture by evaporation. So the concrete tends to lose moisture, making it look like making it dry, which is which looks something like this. So you can see here a surface of a concrete that is actually some point dried out because of the evaporation of the moisture that it contains. The opposite of that phenomenon, the drying shrinkage, is the volume increase through water absorption and is termed as swelling. In other words, shrinkage and swelling represent water movement out of or into the gel structure of a concrete specimen due to the difference in humidity or saturation levels between the specimen and the surroundings, irrespective of the external load. So shrinkage, unlike creep, is not dependent on the load applied to the material, especially the concrete. So creep is dependent to the load applied, but shrinkage is not actually dependent to the load, but rather to the movement of water in and out on the concrete. So again, the evaporation of moisture from the concrete is what we call drying shrinkage, and the absorption of water by the concrete, therefore increasing its volume, is what we call swelling. Drying shrinkage occurs after the concrete has already attained its final set and a good portion of the chemical hydration process in the cement gel has been accomplished. So that is when the drying shrinkage occurs, after the concrete has already attained its final set. So if we will try to graph the relationship of the strain due to the shrinkage with time, it will look something like this. So at time is equal to 0, there is no shrinkage strain, but as time goes by, the strain being experienced by the material or the concrete increases with actually reaching a certain limit here. So that this is the relationship between the shrinkage strain with time. The rate or the slope decreases with time since older concretes are more resistant to stress and consequently undergo less shrinkage, such that the shrinkage strain becomes almost asymptotic with time. So you can observe here on the graph that the slope of the curve, or in other words, the rate of increase of the shrinkage strain with respect to time decreases as time goes by, with actually reaching a certain limit here. Certain limit, it tends to be asymptotic with time when it reaches this certain limit here. With older concretes manifests more resistance to shrinkage strain, with the same reason as what we discussed on creep, since it already attained its its strength the older concretes. So there is a way to compute shrinkage strain, but the formula we will see here are only applicable for standard conditions of humidity, which is humidity equal to 40%. So for moist cured concrete, the formula for shrinkage strain is this, with the value of this. This is the ultimate shrinkage strain. You can use this value if local data are not available. For steam cured concrete, you can use this formula, almost similar to this. We just change the 35 to 55, and you can use this ultimate shrinkage strain with this value if local data are not available. So may I just repeat, these formulas are just for standard conditions of humidity, which is 40% humidity. So for other humidity, there must be a correction factor to be applied here on this magnitude of the shrinkage strain. So what are those correction factor? For humidity greater than 40% but less than or equal to 80, you can use this correction factor. But for humidity greater than 80 but less than or equal to 100, you can use this correction factor. So how to use those factor? You just have to multiply this magnitude, this value that you will get here, to the magnitude that you will get here. So that is how you correct the shrinkage strain using this correction factors. If the humidity is not standard or in standard conditions of humidity, which is H is equal to 40%. So as you can see on what we have discussed, we have discussed the different properties of hardened concrete, which actually those things actually uh, is related. Those things are actually related to the strength of concrete. So when designing, we don't want our concrete to lose a more major portion of its strength even before it will serve its intended purpose, like supporting loads or occupants. So for the concrete, in order for us to make sure that that there will be enough strength that will be remain what will that will remain on the concrete to serve its intended purpose, the code specifies a certain maximum permissible stress that can be imposed to the concrete itself. So if you will base or if you will refer to the ACI code 318M-14, if you will refer on section 24.5.2, uh, the code specifies certain limitations in terms of stress that can be uh, experienced by the concrete at certain stages of pre-stressing, because just like what I've said before, we don't want to overstress concrete as we conduct pre-stressing activities. So the code specifies certain limitations, the maximum permissible stresses at each stages of pre-stressing. Like for example, if for the at transfer at transfer stage of pre-stress, the code specifies certain limitation on the maximum compressive stress that the concrete can experience, which is this. And it also specifies a maximum tensile stress that the concrete can experience at transfer stage. But although the US customary formula for this formula here is actually this. So just for your information. And again, those are just for limitations for at transfer stage. This is the tensile limit, and the other one a while ago is the compressive stress limit at transfer stage. So you have to take note of that. But after the transfer stage, so for example, the concrete is already on service load condition, wherein wherein it already carries the service loads that are intended to be supported by it. The code also specifies maximum compressive stresses as well as tensile stresses that the concrete can experience to make sure that it will not be overstressed and can still serve its intended purpose which is to resist the ultimate loads that is expected or designed to be carried by that particular concrete element. So those are from the ACI code. So if you will refer to our local code, the NSCP C101-15, actually you will see almost the same code provisions, because again, we have our local code has adopted the international code. So if you will refer to AASHTO, actually AASHTO has their own way to limit the stresses being experienced by concrete at different stages of pre-stressing. So like this, for example, before the losses that will be before losses of pre-stress is being experienced by the pre-stressing reinforcement, the code specifies these limits in compression for the concrete, as well as the limits for tension for the concrete. So this is actually the tensile limits specified by the AASHTO 2012 that can be experienced by the concrete at this particular stage before losses occur on the pre-stressing reinforcement or pre-stressing components. So after the losses, so AASHTO specifies these particular limitations on compressive stress that the concrete can experience, as well as the tensile stresses that it can experience at that particular stage after the losses occurred. AASHTO 2012 also has its own way to compute modulus of rupture. So this is the formula for computation of modulus of rupture uh, in reference to AASHTO 2012. So there you go. Those are the things that we have to know about concrete, about the different properties of concrete. So we are already finished there. So after that goal, let's go to our next goal, which is to be familiar with the different properties of non-pre-stressing reinforcement. So let's go there.